So hey guys, this is Kartik and we'll be having a similar video to the ones we have on our channel, but this will be special because I have Gaurav with me. He's here as a guest, and although I'm not going to specifically show him mercy, I'm going to challenge him with a code versus hard problem. Most of you might already be knowing Gaurav, but for the ones who are new to the channel, both to mine and Gaurav's, Gaurav is a software engineer. He's also a competitive programmer. Recently, he started his own company, Interview Ready. He's really good at system design. You should definitely check out his channel, follow his playlist on system design. That is the one that I'm currently following. And for the people who want to deep dive, definitely check out Interview Ready as well. Also, promotion sake, you can use Kartik20 as a coupon code and you'll get 20% discount on his courses. So Gaurav, are you ready to be challenged?
Absolutely, I think I can do this. Yeah, all this red, blue, green doesn't matter. It's all about using this pen on the right board.
Right. I've seen that you're doing algo workouts quite a lot.
Yeah, no, in a controlled environment, of course, but okay.
Okay, then let's get to it.
Let's do this. Yeah.
The problem is that you're given with an array. That array has n elements,
Okay.
all integers.
Okay.
And I'll define a term known as the imbalance of an array. Are you aware of that?
No, imbalance.
Okay.
Like people when they're drunk.
Yeah, kind of. This array is kind of drunk. So, but we don't care.
Okay.
We don't judge people on that. Okay.
Okay.
So the thing is that the imbalance of a segment is, let's say, imbalance of L comma R.
Okay.
L comma R is a segment of the array. Imbalance of L comma R is defined as the max element of L comma R, whatever is the largest element in this range,
Okay.
minus whatever is the smallest element in this range.
Okay. Min of L comma R then.
Yeah, makes sense?
Okay, okay. So if I take an example, if I say 3, 0, 1, 7, 2, 4, 5, and if I take the imbalance of 0 to n minus 1, so I get the imbalance of this array is the largest is 7 and the smallest is 0, so I get 7 as the imbalance value.
Perfect. It's like the imbalance of this segment.
Of
I'll define the imbalance of the array now.
Okay, okay. So yeah, it's for a segment of L comma R. So if I took the full array, then I get this thing. Okay. Now you have imbalance of array also. Okay, imbalance of segment is equal to max of segment minus min of segment. Okay. And you also have imbalance of array. What is that?
Okay. So now you know the imbalance of a segment.
Yeah.
Imbalance of the array is for each and every segment that exists in the array.
Okay.
Find out the imbalance of every segment and add them. That's it. Simple problem.
Okay, okay. Imbalance of all segments in
Of
this
this
array for all segments. Okay.
Right. And what you want to do is you want to find the imbalance of the input array.
I'm sorry. You want to find the imbalance of the input array. This one, A.
Exactly. So given the array, just find the imbalance of the array and you're done.
Okay. Okay. So if I have to find the imbalance of the whole array, that means I have to find for every possible segment, which means I have to find for n square arrays.
Okay, so for clarity's sake, let's take a small example so that we are on the same page.
Yeah, yeah. Let's take the example 301.
Perfect.
Okay.
So try to find the imbalance of this and we'll know whether we are on the same page or not. Majorly consider all these segments and add their imbalances together. That should be the answer. So for example, in this one,
Yeah.
you'll get 3 plus 0 plus 1. I've considered the segments of size 1.
Yeah. So, okay. So you have a segment of size 1, which is 301. This is the easiest. Segment of size 2, 3, 0, 0, 1, and that's it. Yeah, that is right. And the segment of size 3 is just one of them, which is 301. Okay. Now, if you want to find the imbalances, this is max is 3 minus 3. So this is basically this is 0. This is also 0. These are always 0. Segments of size 1 is 0. Okay.
Yeah.
Apart from that, this is 3 minus 0, which is 3.
Right.
1 minus 0, which is 1. So in
Right.
total we have 4 over here, and then we have again 3 minus 0 only, which is 3. Okay, so I'm seeing that there is some sort of maybe movement going on from here to here, but let's see if that happens. We have basically 3 plus 1, which is 7. So imbalance value of this array is 7.
Perfect. So I think we are on the same page and we understand the problem now.
Okay, okay. So firstly, let's say that I'll just do a brute force solution so that things are simple. There are n square subarrays for any array of size n. So from how many subarrays can you make? That is nc2, which is n into n minus 1 by 2. Like over here you had 3, so that was 3 into 2 by 2, that would give us 3. We got 6 instead, but that is kind of fine because I mean we can make it n plus 1 by 2, in which case this is n plus 1 c2. But actually I like the previous formula because what's happening is that I'm losing out on n arrays which are contributing nothing to my sum because these are always 0. So what I could do is I can just say take nc2, these many subarrays I have to take into consideration, okay, and every subarray's max and min can be calculated using a segment tree.
Okay.
I can keep a segment tree which will tell me for any range L comma R. So I'm already using the heavy data structures already, but
You kind of scared me off.
if I want to find the min of left to right of any segment left to right, a segment tree can give me that in order log n time. And
Perfect.
yeah. So guys, if you're not sure what a segment tree is, you can have a look at the links in the description. But you can get min and max by pre-computing mins and maxes in every segment, and then for any random range you can get it in order log n time. Okay.
So perfect. Let's just assume we know how to build a segment tree.
Okay. So now comes the point that you have n square subarrays approximately. This is n square approximately, and we get n square into log n as the overall time complexity. This is the brute force. I don't know whether I should call it brute force. It uses segment trees already, but yeah, this is like one possible time complexity. Is that?
I think that's perfect. Previously, what we were doing was the way we solved the example. That felt like n cube. You would like pick out each and every subarray, then you find the min and the max, and finally evaluate the answer. So I think that was n cube.
That was actually, yeah, you're right. Yeah, that was n cube. That was brute force. So I've improved it to n square log n already. Like this is a big improvement. But okay, let's see whether we can do better.
Sure.
Okay. If you want,
let's try n square, but let's try to eliminate that segment tree off. Can we do that?
Okay. Can we get rid of the segment tree? Okay. Heading back to the original array. Let's see if we can find some patterns. So when we said that we need to find the imbalance of an array or of a segment, we are taking the max in that segment minus the min in that segment. So okay, there's two special elements here. First one being that the max of the entire array, let us say it is 7. How many times does it occur?
Okay.
It occurs every time. Every time you touch 7 in your subarray, anytime, like this is index number 0, 1, 2, 3. So anytime you have 3 in the range of left to right, the maximum turns out to be 7. Okay, so what is happening here? Actually, every subarray is being checked for its max and its minimum. So if I can take all the subarrays maxes and just keep them here, like basically keep on doing a plus for every max that I find, and all the subarrays mins, and keep doing a minus for all of them that I have, then I'm done with the problem.
Okay, I think on surface level that sounds good.
Okay.
But I think we should prove it.
Okay. how do we prove it? Let's take it this way, right? Let's take it that the number of max. I mean, which max are we taking? We are taking for any I comma j, all the max, and we are doing minus min of I comma j, right? These are the indices, left and right indices. So we are taking a sum of all of them from I equal to 0 to a particular point n minus 1, and then we are also doing inner summation j equal to I plus 1 to n minus 1. This is the thing, right?
Yeah. Perfect.
So yeah, mathematically, if you pull this stuff out, you can do the double summation outside. I mean, each of them. So if I'll just mark it as double summation. So max of I comma j minus double summation min of I comma j. This should work because we are doing a simple operation which is minusing.
Okay, let me just rephrase. So majorly the first formula that you have written, that is nothing but imbalance of the array, the initial formula we discussed.
Right.
And the inner part is the imbalance of a segment.
Yeah, so the imbalance of a segment defines the imbalance of an array by taking the sum of all the imbalances of every segment you have.
Okay.
So I just took this thing and I expanded it. So I took a sum over here, which is here outside, and the maximum of a segment minus maximum of a minimum of a segment. So that is over here.
Oh, got it. So from what I understand, that max minus min represents your imbalance of the segment, and those two summation basically indicate each and every subsegment out there.
Yes, yes. So like we said, n square segments exist.
Perfect.
Right. So I to j. Okay. So if this is the case, then I can make this a little simpler. I don't need to do this calculation separately. I can break these calculations. How can I do that? Well, I want max of I to j for all ij. So if I can take the frequency of a maximum occurring element. So let me explain this a little clearer. Let's take 7. Okay, this is the maximum in the array. How many times does it occur in this equation? It will occur the number of times that the number of times that it is a part of a subarray. So that is 1, 2, 3, 4, 5, 6, 7. So it occurs 7 times. N is equal to 7. It occurs 7 times. How many times does 0 occur as a minimum in the array? It occurs 7 times because there is nobody challenging it. Anytime it is part of a subarray, it is the minimum. Does this part make sense?
Yeah, I think it's making some sense.
Okay.
What you're doing is that max ij, that inner portion of the formula that you've written.
Yeah.
You're trying to find out that how many times is max ij equal to 7. Is that what you're doing?
Yeah. So it becomes a very simple thing. Frequency of any element a of I as max. So the number of times it is maximum, this element a of I, minus the number of times that it is minimum, is the answer that we are looking for. And this is for all I.
Perfect. Let me just convince myself.
I equal to 0 to n minus 1. Yeah, this is what we need to do. The reason being that we don't care about this entire formula. I mean, we do care, but the transformation of this formula gives us that how many times do you occur as a maximum element, how many times do you occur as a minimum element. Whenever you occur as a minimum element, I need to subtract, and whenever you occur as a maximum element, I need to add.
That max of any segment is going to be one of the elements of the array for sure. So max of ij is going to be an element of the array.
Yes.
Okay, so it makes sense that in how many subarrays was this the maximum, and then you take them and add them.
Right. So that's all we need to know. How many times have you come as a maximum, and how many times have you come as a minimum? I'll just do this and I'm done. So okay, like at least this is going to be order n because this is the number of things, but I need to now quickly find how many times have you occurred as a maximum in the subarray.
Right.
Okay. So if you have 7 as the largest element and the second largest element here was 5. So 5, I don't know how many times it occurs. It depends on the position of 7. So I need to find, in fact, for 4, then I need to find the next largest element to the right and the next largest element to the left.
Okay, I think that is making some sense, but let's try to do this in a general way. Imagine that you're trying for the element E. Then can you explain me what's the thought process to find out the number of subarrays in which E is the largest?
Okay, so if you take a general element E, in this case I'm taking this as the general element. But when you have a element E, so A of I is equal to E.
Right.
I need to find the index j, which is less than I, and because I'm searching for max, A of j is greater than A of I. I'm just thinking, what if they are equal? What if two elements are equal? What do I do then? So the max minus min in that case is still okay, right? Because you're still part of the maximum in that subarray also. Okay.
Let me make it a bit easier for you right now. Let's assume that all elements are distinct.
Okay.
Although the problem can say that they might be equal, but for now let's try to solve it for distinct, because then it's pretty much straightforward.
Yeah. Then this is the thing that I'm looking for on the lesser index, or the left index rather. This caps out A of I. So A of I, if this is A of I keep heading towards the left and I find an element which is greater than me, I stop here. This is my safe space. Then similarly, I say j is greater than I and A of j is greater than A of I. I need to find such an element, or I can call it k. So that will make it a little easier to think of. So I keep heading to the right and I find a k. In this particular case, k is already over here, so this is my segment.
Got it.
So now this is the place where 4 is occurring as a max. It's occurring as a max over here, and it's occurring as a max in this large array also. Now if we go to the previous thing, 4 occurs as a max here once, twice. So I just need the size of this segment. So now that we have these two indices, j and k, what we need to do is we need to create subarrays. Okay, so let's say this is I. I went to the left, I found a j, and I went to the right and I found a k. Okay.
So are we trying to find out the number of subarrays in which I is the max? That is the goal.
Yes, right? Yes.
Assuming that we know j and k already.
Yes. So to find the j element and the k element, this is what we did. Let's say we went brute force. We went one by one to the left as much as possible till this condition was met, and then we went to the right as much as possible till this condition was met. So we have two indexes which are elements greater than us when we are standing at I. Okay, so this means that the number of times that I occurs as a maximum element is going to be all the subarrays which is containing this element I. I exist here, and then these are all the elements over here. Okay, so let's try to see how can this work. There are sometimes there's going to be an array also which is of like this also. So there is some sort of overlap and stuff here. So okay, actually this is quite interesting, because the number of starting positions can be from here to I, right? Starting, and the number of ending positions can be from I to this point, j. So this is j, this is k. So from k to I, rather from j to I, you can have starting positions, and from I to k, you can have ending positions.
Okay, right. So basically what you're saying is that the subarray starts from one of the points, starting from the
left side.
I.
Yeah.
Okay. Perfect.
And ends at one of the points on the right side.
How many subarrays exist which start from the left and end at the right? That's the idea.
Yes, that would be I minus j minus 1. And this would be into the total number of positions you can start at on the right. So that is k minus I minus 1. Let me see if minus 1 actually comes in here.
So yeah, just one nitpick here.
Yeah.
Actually, your subarray should not start from j, but from j plus 1. But that's fine.
Oh, okay. Yes, of course. And it should also end at k minus 1.
Exactly.
Right. That makes
that's
sense.
fine. Yeah.
But maybe through this formula itself we can
adjust that.
So okay, this is actually interesting because now we have the maximum frequencies given efficiently through this. How much time does it take me to find a maximum frequency for any element I? It takes me order n time. Okay,
Fine.
and because I'm doing this for n elements, it's going to take me overall order n into n, which is order n square, which is better than order n square log n. But I think I can do this faster also.
I think this is perfect. This is much better than your n squared log n, and like you eliminated the need of a segment tree.
Right. And also like if we just use what's happening here is that if I put these elements in a binary search tree, a BST, the reason I'm doing this is because I need to find the next greatest element from a particular position. So I can use something like a tree map or something.
Okay.
And I can say what is the next greatest element to the right hand side.
Okay.
So now let me think about that again. The next greatest element to the right hand side of a particular element A of I.
Your query is, hey, tell me what's the next largest element to the right
element for A of I. Yeah. So one of the things is I can be a little like clever about this. I start with the largest element. Okay. So first I take 7, which is the largest element. I find there's nothing to do. Basically, this is the largest element for everything, right? So okay, there I do nothing. Second largest element, in our case 5. Now what we need to do is we need to find the largest element to the left and right. But I know that this is this, so I can store 7 in the BST now, because it's the only guy who can be greater than 5. So 7 has an index of whatever was the index. It doesn't really matter much, but I'll just note it down. It is 3, index of 3. And so now 5 comes here. 5 says, what is my index? My index is 6. Which element is greater than me and has an index greater than 6? It comes here, says nothing. Okay. And which element is greater than me and has an index less than me? So that is 7.
Okay, fine. I think this will work. This will work.
No. I don't need to store the values only. Actually, this was not a very smart thing. I don't need the values. I don't care about the values.
I need the indices.
Yes, absolutely. So
perfect.
6 is the index, and you have 3 over here. We come here. Find me the greatest index greater than 6. Oh, I'm the greatest. So basically, the end of the array. Till that point, I'm the largest. So right. And over here, when you say smallest, well, 3 is here. If there was something else also in this tree, if we could, 3. So the greatest element less than me. So 3, and then I would say, okay, 3 is actually smaller than me. So is there something to the right also? And if there was, let's say, if there was 4, then I would choose 4. Okay, so actually let's just run through the problem once so that it becomes even more clear. The idea is pretty simple. Initially, I have 7 being picked up. Okay, so 7 is the master of this array. It occurs in every segment or to the left and to the right. So this size is 4, and this size again is 4. So 4 cross 4 are the total number of starting and ending indices. So this is like, it occurs 16 times. Okay, roughly.
Perfect. Yeah, I think that is exact.
Right. So now comes the second array. But before that, we actually have a binary search tree where we have pushed in 7. The index of 7 rather. So index of 7 here is 3. I push in 3. The next element, when I'm going in a sorted fashion, because I'm taking maxes all the time, I take the second largest element, which is 5. So for this, I just need to sort the array, which is n log n in time. And then I pick up the second largest element, which gives me 5 has an index of 6. So 6 is here. I ask which element is in this BST having an index less than 6. Okay, so what is the closest element less than 6 in this BST? So I come here, I come to 3, I say okay, 6 is actually greater than 3, so I will be going to the right hand side, and I get nothing. So the closest element to the left hand side is 3. That makes sense. This is the point.
Okay.
While I now say, okay, which element is greater than me? That doesn't exist only because I go to 3. Okay, I want to get an element greater than 3. I go to the right. Again, I get nothing. So 6 is actually the largest element. This is what I have. So now that gives me a size of, the second time when I ran the thing, I got nothing. So that is one combination. And the first time I ran the thing, I got 3 possibilities. So into 3. So that is 3 subarrays where it is 5 is the largest.
Okay, fine. So what you did was closest to left and greater than it. Since the BST only contains elements that are greater than 5,
yeah.
So you just need the indices and not even the elements.
Exactly. I don't even know which elements actually exist in this BST, but I do know that because I'm heading in a sorted fashion, all elements which have occurred here are greater than me, and therefore the indices closest to me are the ones I'm looking for. They will be greater than me, and within them I am the king. I'm the person who has the max.
Okay, this makes perfect sense. And also, just for the sake of implementation, you can replace that BST with a set of integers maybe, and then your query can be done using lower bounds and upper bounds.
Okay. Yeah, we could use a set. Yes, you're right. So worst case of BST is order n square, but n log n. I mean, this is a set will give us log n for every query. There are n elements, so n log n is totally fine.
Yeah, set is anyway a balanced binary search tree, so it's good.
Right. Okay, so that makes sense, and we cannot improve on this using this algorithm because we are already going at we are sorting the set, so that is n log n.
Yeah, your sorting is anyway n log n, so no matter what structure you use later on to find the closest to left and right, it doesn't matter.
Yeah.
Okay.
Is there any way to find the closest? Yeah, I mean n log n is pretty good actually. So
actually, this is decent. This is more than decent. But in an interview, you would like to do the best. If you were at codeforces, you would have been more than happy. You would have submitted it. That's why I like codeforces.
So there's something better than this also.
Yeah.
Okay.
So see, there's a standard interview problem. Let's forget about this entirely. This standard interview problem, which is quite famous. You'll find it on most of the coding sites that teach programming for interviews. The problem says that for every element, find the element nearest element greater to it on the left.
Okay.
And that's the problem. Okay. And it's actually solvable in OM. What you said does solve it in log n. But if you forget about this big chunk of problem you were solving and just focus on this small piece, maybe you'll be getting some ideas.
Okay. So, yeah, I used a binary search tree because it is pretty fast at finding the nearest position when you have a sorted set of things.
So the clue from my side could be try going from left to right, and for every element see what was the nearest element to the left that I saw which was greater than it. And you can try doing it on the array right now. So for this example, when you're standing at 3, you know that, okay, there is no element to the left that is greater than it. So probably -1 or the left boundary of the array.
Yeah.
Then maybe for 0.
You're saying that there is a way to quickly find this range, and there is a way to the idea that you're saying is that there is a way to quickly find the nearest element which is greater than me to the left, and the nearest element which is greater than me to the right.
Perfect. But focus on only one of these for now, and we'll see how the other one can also be done. So let's just focus on left side.
Okay. Let's say that we can mirror it for the right one. Okay. So for any set of numbers, we basically want to find all the elements that this array contains and their minimum elements to the left. Okay, so let us take 3. What is the minimum element to the left? Well, just me. Okay, that is good. That's an easy one. 0. Which element is greater than me and to the left? 3. Okay. What about 1? Greater than me and to the left is still 3. Yeah. 7 is still 3. No, actually you're not greater than me. So actually I have to go all the way to the left here, and I become the greatest now. Okay. And similarly 2, you become the greatest. Okay. So I'm getting an idea that something like a heap might help, but heap is not going to help the overall time no, it will actually. The heap will help the overall time complexity. It will be order 1 for getting max. Or I'm wondering whether, okay, but in a heap, when I'm inserting an element, it is log n.
Right. So
it's not helping.
Stay n log n.
Yeah, n log n. But constructing a heap is,
that's big O of n.
Yeah, that is big O of n, but you have to build the heap, I think, together or something. From what I remember.
Right. Yep.
Yeah. No, that won't help. Okay. Just one element has to be kept. What if I use something like a stack?
Okay.
Let's say this is what I have. I have initially 3. I get 0. So now that 0 is, so with 0, what we do is we see that 3 is greater than us, and we note that index down. Basically, we can go up to 3 or less than 3, but we also add 0 to the stack, because it could be that an element lesser than 0 comes next. So we'll see how that works. Okay. Now next comes 1. 1 comes into the stack and sees 0 is actually less than 1. This is an interesting thing. We actually kick out 0. Okay, and we insert, we see 3. 3 is greater than 1. Okay, that's my largest element now. So that gives me the position that I need to go to the left hand side.
So I have one query here. Why exactly did you kick out 0?
So because we kick out 0 because it's never going to be that an element to the right hand side is going to actually see 0 as the largest element. It will see 1.
Okay, because if there is an element,
3. Yeah.
Okay, fine. Because if there is an element to the right that is even smaller than 0, then definitely it's smaller than 1.
Yes. You can get 2 now, which is going to kick out 1, but 3 will remain. So I will then kick out 1 and then push in 2. So this will be the stack position if that 2 occurs. Okay, and I'm kicking out elements only when I know that there is no way that on the right hand side there will be an element which will touch 0, because to the right of 0 we have 1 which is greater than 0 and is closer to them. Okay. Does this part make sense?
I think this is perfect. This is the actual standard solution to the standard problem.
Okay.
But one thing here, could you prove why this is ON?
Yeah, so what's happening is I'm kicking out an element that is just happening once. So if an element, how many times am I inserting the element? The number of times an element can get kicked out is 1, n elements, so that is order n, number of kicks. How many insertions do I have? Well, when I insert this element, let's say 7 comes here, I see that this element is less than kick out. The number of times I can insert the element is also 1. It's just happening when I'm actually checking the element. So that is also order n inserts.
Exactly.
Right. So this makes this okay. This is order n then.
Perfect, because each element will go once into the stack and at most once out of the stack.
Right. So this is the concept of flow sort of thing, that you can enter only once. And you can exit only once, and because there are n elements, you have 2n computations, the rest of the computation is also O1, basically finding the largest, finding an element which is larger than you to the left and closest to you. So okay,
you just need to check the stack for that.
Yeah, I think you will need to do this for max twice, left and right, and for min the same number of times. So you need 4 stacks. You don't need 4 stacks. You can use the same stack, reuse it, but you need 4 times you need to do these operations. So order 8n, if you're doing this 2 2x. So that is again order n.
Perfect. Got it. So nice. I think that makes sense. Initially, since we're able to evaluate like in O(n) time, closest element greater to the right and to the left, and then we are able to multiply that by the formula you derived, we can do this for every element and we'll be done.
Yeah. This makes sense. I think the most important thing in this problem, like this is a very elegant solution, the stack, but the most important thing is finding out that I can go to the left and right and just count the number of times I occur as an element in max or min.
Exactly. I also feel that the most important thing was the observation that you can like multiply the frequency with the maximum. How many times this appears as the maximum minus how many times this appears as the minimum.
Right. Actually, this will be then we have to multiply this whole thing by a of I, because it's occurring these many times and these many times, and this is the value.
Right.
Okay.
Exactly.
Interesting.
Perfect.
I missed out on that, but yeah. Okay. So
I hope you were challenged enough.
Yeah, tremendously, I should say. But yeah, this is a very interesting problem. It's in fact perfect for an interview setting. Again, people can give order n cube solutions, like if they want to fail. N square log n is okay, but order n log n is actually pretty good. I would say like this is a higher, and if you want a strong higher, then go for this guy.
Right. I think even n log n is kind of a strong higher if the person is able to explain that well. That is a brilliant solution.
I think this will be, you're right, this will be around 4 or 5 out of a score of 5. This will be 5. This is like maybe 2, and order n square, like I would be surprised if they couldn't come up better than order n square, but that would be like most likely a tentative higher. So yeah, and order n cube is like, okay, person needs to go home now. Pretty brutal.
Okay, so nice. In fact, not talking from an interview perspective, this is actually not a very easy problem even on codeforces. It's rated 1900. Okay. So what that actually means is that if a candidate master tries to solve this in a contest, there's like a 70 or 80, 75% chance that he or she will be able to actually solve it in the contest. So that is like how the rating measures.
Okay. Interesting. Okay, that's interesting. And this is a pretty decent rating, no?
Yeah.
Okay, and like, solve would be like n log n. So, yeah.
So I hope you guys enjoyed the video and you were able to understand the solution to the problem. Honestly, it was not that easy. Especially understanding and explaining were the harder parts. So Gaurav did quite well there. Also, let us know in the comments which part you liked the most, which part you did not like. Bata dena marzi hai. But yeah, definitely subscribe to the channel. Check out Gaurav's channel and also check out Interview Ready. See you again. Bye.